Hello everyone, we are Greenergy. Today we will report on thermal optimization of anaerobic digestion. Our project focuses on future grains compact anaerobic digestion system for breweries and food manufacturers. The system transforms unavoidable organic waste into renewable on-site energy, supporting both profitability and sustainability through circularity. The key challenge lies in the thermodynamic performance of process, as heating, cooling, and fermentation demand high thermal energy, causing efficiency and costs. Our task is to conduct a thermodynamic and techno-economic analysis, identifying opportunities for heat recovery, efficiency gains, and cost reduction. In addition, we will assess the market potential and customer demand, ensuring the technology not only performs technically but also achieves commercial competitiveness and adoption. Next, I will briefly introduce the members of our team and what they are responsible for. Faria leads the thermodynamic analysis, calculating heating and cooling loads, mapping the system's overall energy balance, and identifying the most energy-intensive stages for optimization. Risa conducted the heat recovery opportunities analysis, identifying recoverable energy from cooling stages and proposing integration strategy to reduce external heating demand. Liu focused on the equipment selection for heat recovery, researching feasible technologies such as spiral heat exchangers, plate heat exchangers, and heat pumps, and evaluating their technical suitability and costs. Yash performed the market analysis, profiling the UK brewing sector, identifying customer demand, adoption barriers, and competitor positioning to determine future grains commercial opportunities. Iftikhar carried out the techno-economic feasibility assessment, evaluating capital costs, operation savings, payback potential, and long-term commercial viability of implementing heat recovery system. Our presentation will cover four main parts. First, the thermodynamic analysis, identifying the system's energy demand and efficiency. Second, the heat integration and equipment selection, exploring opportunities for energy recovery and the choice of the suitable technologies. Third, the techno-economic feasibility, evaluating costs, saving, and overall viability. Finally, the market analysis, assessing customer demand and competition and adoption potential. Well, next, Faria will talk about her part.
To present a thermodynamic analysis of future grains anaerobic digestion process. The aim of this analysis was to calculate the heating and cooling requirements for each stage of the system, and then establish the overall energy balance. As shown in the diagram, the process starts with the spent grain and water entering the liquefaction tank, which heats up to 90 degrees and then cools down in two stages. This is then mixed with beverage wastewater before being conditioned to 37 degrees, which is the operating temperature of the EGSP reactor. I used heat capacity of 4.18 kilojoules per kilogram per Kelvin, assumed an ambient temperature of 15 degrees, and neglected any heat losses through the pipe network. The two equations shown are the governing equation. The first one calculates sensible heat changes, and the second one balances the energy exchange during mixing between hot and cold streams. In stage 1, the slurry is heated from 20 degrees to 90 degrees. Applying the formula of thermodynamics, I get the heat requirement of 528 kilowatts per hour per day added. This is the second largest heat input in the process. In stage 2, the slurry is cooled from 90 degrees to 55 degrees. This removes 950,000 and 150 kilojoules per day, which are equivalent to 264 kilowatts per hour per day, which represents a significant amount of recoverable waste heat. In stage 3, cools the slurry further from 55 degrees to 45 degrees, removing 275,700 kilojoules per day, or 75 kilowatts per hour per day. Together, the two cooling stages release around 239 kilowatts per hour per day of recoverable heat energy that could be reused later in the process. In stage 4, the hot slurry from vessel 1, which is 6,500 kilograms at 55 degrees, is mixed with 54,000 kilograms of cold wastewater at 15 degrees. Using the energy balance equation, the resulting mixed temperature is about 19.3 degrees. After mixing, this combined mass must be heated up to the reactor's required temperature of 37 degrees. To achieve that, I calculated the energy needed using the same heat equation of roughly 1,243 kilowatts per hour per day, which are added. This is the largest energy demand in the system, accounting for more than 70% of the total heat input, making it the least efficient stage and the key area for future improvements. This table summarizes the total heating and cooling values for all 4 stages. Stage 1 and 4 require heat input, while stages 2 and 3 remove heat. When all stages are combined, the process requires around 5,155,000 kilojoules per day of total heat movement, with a net external heat input of about 1,432 kilowatts per hour per day. This means that without any heat recovery, the system depends heavily on external heating. However, the rejected heat from stages 2 and 3 provides a valuable opportunity for energy recovery, which could reduce the net energy input by up to 25%. Overall, these thermodynamic analyses provide a solid baseline for identifying inefficiencies and guiding the design of the heat recovery system in the stage of the project. To conclude, these calculations highlight exactly where energy is consumed and wasted within the process. This information forms the foundation for the upcoming heat integration and techno-economical analysis, where we explore how to reuse this waste heat to make the system more energy efficient and cost effective.
Hello, my name is Raisa, and I'm going to be going through heat recovery opportunities within this process. As we know, vessel 1 goes through 2 cooling steps. First, it cools from 90 down to 55 degrees, and then from 55 to 45 degrees. Every time this cooling happens, a large amount of heat is released, but at the moment, this heat is just lost to the environment. After this, the hot slurry is mixed with about 54 cubic meters of cold wastewater at around 15 degrees in the recirculation tank. Because the wastewater is much colder, this mixing can cause the overall temperature to drop very quickly, which can be a problem because the EGSB reactor that comes after needs the liquid to stay close to 37 degrees, as the microbes inside the reactor are very sensitive, and if the temperature is too low, it can shock them and reduce the efficiency of the process. So we need to find a way to reuse that wasted heat to keep things stable. Therefore, we identified 3 main opportunities. First, the high-grade heat release from the cooling between 90 to 55 degrees. This can be the useful heat, and it can be used to preheat either the incoming wastewater or the fresh batch water needed for the next cycle. Second, the medium-grade heat release from 55 down to 45 degrees. Although this is lower in temperature, it can still be used to gently warm streams that don't need to be as hot, such as the influent before it enters the EGSB reactor. Third, the mixing point in the recirculation tank. If we preheat the cold wastewater before it mixes, we can prevent such a sharp drop in temperature and protect the microbes inside the reactor. However, in total, we found that heat recovery could save about 339 kilowatt hours per day, which covers around 27% of the total heat demand. So while it doesn't meet the whole demand, it still represents a meaningful saving. Thus, to actually make this work, we would need extra equipment such as heat exchangers and possibly an auxiliary heater to cover the gap. That way, we can capture this wasted heat and reduce how much external heat energy is required.
Hello everyone, this is Liu. I will now present section 2.2, the core equipment required for our heat recovery system. We evaluated 4 key categories of equipment. Let me briefly outline their pros and cons. First, for plate heat exchanger, pros there are unbeatable thermal efficiency in a compact footprint and easy to open and clean for maintenance. And for cons, there are narrow flow channels are highly susceptible to clogging with fiber solids. This is a critical weakness for our applications. And second, for spiral heat exchanger, pros there are long single flow path is ideal for slurries with solid, has a self-scouring action that resists falling and clogging. And for cons, it's generally larger and more expensive than a PHE for the same duty, and cleaning can be more involved. After that, for industrial heat pump, it's a supporting component for upgrading low-grade heat, but it cannot handle the primary task of transferring heat directly from the dirty slurry stream. And for ancillary components, like tanks and pumps, are essential for support. They don't perform the core heat exchange itself. This is why we selected the spiral heat exchanger as our core unit. It was the only option designed to handle our tough conditions. Its long single-flow path and self-scouring action prevent clogging, ensuring reliable, continuous operations between the 2 dirty streams. Here's a workflow it enables. Firstly, 90 degrees Celsius hot slurry enters the SHE's hot side, and it's cooled to 45 degrees Celsius, releasing its heat. And next, this energy is directly transferred to preheat the cold 19.7 degrees Celsius mixed influent on the cold side, and then the influent is warmed to approximately 24.1 degrees Celsius, reducing the final heating loads by over 27% before the trim heater brings it to the target temperature. In summary, by selecting the right tool for the toughest job, this design delivers a major energy saving and stable reactor operation.
Now, moving to the technical feasibility, our goal was to make the digestion system much more energy efficient by capturing waste heat from different process streams. We identified where heat losses occur and explored recovery solution using heat exchanger. The improved design aims to minimize waste heat, reduce dependency on external heating source, and make the overall system more sustainable and cost effective. On this page, we can see that the design improvements which are made to enhance the performance. The new setup minimizes waste heat and optimizes heat exchange between process stream. It not only lowers the operational cost but also improves environmental sustainability. The graph on the right hand side shows how the capital cost of the heat exchanger changes with its length, helping us to choose the optimal size for both cost and efficiency. The top graph shows a plate heat exchanger image as an example of efficient and easy to clean equipment which was used in our proposed design. Here we can see a detailed flowchart of the heat recovery scheme. We identified where heat can be extracted and reused. For example, from the hot slurry, leaving vessel 1 to preheat the incoming feed. Using a combination of heat exchanger and possibly a heat pump, the system recovers and reuses the energy that would otherwise be wasted. This helps to maintain the reactor's temperature more efficiently and reduces external heating requirements. Finally, we analyzed the financial opportunities for the whole system we have designed. By recovering almost 27% of the process heat, we can significantly reduce the operating cost. The system can also integrate sustainable energy resources like biogas for heating, further improving the profitability. While the capital investment or capex increases slightly due to additional heat exchanger, it is offset by lower operational cost or OPEX and a faster payback period. Overall, the proposed design is both technically feasible and economically attractive, supporting the Future Green's goal to sustainable on-site energy generation.
Hello everyone, I am Yash Gupta and I am here to present market analysis. The UK brewery sector is facing a crisis. According to the C by UK Brewery Tracker, the number of breweries dropped from 1828 in January 2023 to just 1715 in 2024. That's over 100 closures in 1 year. The northwest and northeast regions were hit hardest, with net closure rates of 14 and 9 respectively. The reasons? What could be the reasons behind it? Legacy COVID debt, rising production costs, and limited access to market through pubs. Setting up a microbrewery is expensive and highly variable. Costs range from £1,000 to £1,000,000. Equipment alone can cost around £40,000. Other major expenses include utilities, rent permits, branding, and professional services. Marketing is especially critical, and with alcohol brands spending over £6 billion on advertising in 2024. Future Greens is a startup aiming to support SME breweries with a compact, integrated waste treatment system. Unlike traditional solutions, it handles both solid waste like spent grain and wastewater, a major differentiator in the market. Compared to other competitors, Future Green offers 10 times smaller footprint, lower capital costs, integrated treatment of both waste systems, potential to recover up to 50% of breweries' energy needs. It's designed specifically for small and medium-sized breweries, making it highly relevant in today's market. To succeed, Future Greens must validate its technology through pilot projects, emphasize quick ROI and low maintenance, match other competitors' ease of deployment while offering superior value in energy and disposable savings. In conclusion, Future Greens is a uniquely positioned to address the challenges faced by SME breweries. Its compact, cost-effective, and integrated solution could be a game changer in struggling industry. Thank you.